Welcome back, everybody. This is our video solution to problem 3 from quiz 5. This is fall 2023, Math 307, Linear Algebra at Cal State Fullerton. All right, let's see what we got here. We have a vector space V over a field F, and we have a basis L given by V1 through Vn. So we have a nice n-dimensional vector space. We define we're asked to define an explicit isomorphism from the vector space V to Fn. So Fn here is the vector space of n by 1 matrices with entries in F. So these are just column vectors, right? So you're going to have something that looks like A1 through An. That's an n by 1 matrix. Okay, and each of these A's should be in F. All right, so define an explicit isomorphism, all right? Now, we should know right off the bat that they are isomorphic. Why? Because V has a basis of length n. So the dimension of V is n. And Fn is an n-dimensional vector space. And two vector spaces with the same finite dimension are isomorphic. But this doesn't say to prove that they're isomorphic. It says to define an explicit isomorphism. So that means we need to actually give a linear map, which is injective and surjective. So here's what we're going to do. First, I want to define some linear map T, right, from V to Fn. And I'm going to define a linear map by just defining it on a basis, right? The universal property of a basis says that's good enough. Okay, so we want a linear map T that is bijective, so injective and surjective. Okay, and so by the universal property of a basis, it's enough to define T on a basis of V. So there exists a unique linear map T from V to Fn. Well, doing what? Well, I need to tell you what each of these vectors from the basis does. And where I'm going to send it is just to what we call EI, the ith standard basis vector. So this is going to have a 1 in the ith row and a 0 in all of the other components. Okay, so we know that that is some linear map. And something very nice about this linear map is that if I take this list E1 through En, this is a basis for Fn. Okay, this is the standard basis. Okay, but that means that every element of the basis is in the range. So this tells me that E1 through En is in the range of T. But the range of T is a subspace, which means it's closed under linear combinations. So the span of E1 through En is contained in the range of T. But what is the span of E1 through En? Well, E1 through En is a basis of Fn. So the span of E1 through En is Fn. But the range of T, of course, is a subspace of Fn. And so we have Fn on both sides of this chain, and so we can conclude that the range of T is equal to Fn. Well, the range is equal to the codomain. That means T is surjective. All right, now, it's actually enough when you're talking about vector spaces of the same dimension to show that a map is surjective, then you'll get injective for free. But let's just verify it using the rank nullity theorem or the fundamental theorem of linear maps. So by the fundamental theorem of linear maps, well, what do we know? We know that the dimension of V is equal to n, but the dimension of V, the domain, is equal to the rank, so the dimension of the range, plus the nullity, so the dimension of the null space. But we already established that the range is equal to Fn. That has dimension n. Well, that means that n is equal to n plus some non-negative number. Well, that can only happen if the dimension is equal to 0. All right, well, there's only one space that has dimension 0, and that's the 0 space. So the null of t is 0. But as soon as you know the null of t is 0, that implies that t is injective. So, in total, the universal property of a basis gave us a linear map. We were able to show that that linear map was surjective because it contained a basis for the vector space, right, the codomain, Fn. And then by the fundamental theorem of linear maps, we could use the surjectivity to imply the injectivity. And there we go. All right, everybody, we will see you next time.